are good practices for achieving those results and shared goals, aiming at enhancing human well-being, promoting the common good, and facing imminent global challenges in technologies, environment, and ethics. This is always more and more important, that the fact that very often research requires the cooperation of diverse groups, diverse type of knowledges, and the interdisciplinarities that puts together physics and engineering, which is the basics of our also of our course on engineering physics. Through the pioneering research, Professor Villiers shed light on the intricate interplay between light and matter, revealing the fundamental principle governing electron motion with unparalleled precision. Her discoveries have paved the way for transformative applications, enabling scientists to probe and manipulate matter with an unprecedented temporal resolutions. I would like also to mention that Professor Villiers stands out for her leadership and mentorship attitude that also inspired new generation of researchers, fostering collaboration and driving innovation in the pursuit of scientific excellence. And this is something we aim here at Politecnico too. Her commitment to nurturing talent and foster interdisciplinary collaboration has had a profound impact on the scientific community, laying the foundation for continued progress and discovery. And I'm sure she will be an inspiration for you as well after this presentation and interesting evening. I would like to thank again Professor Anne Villiers for joining us today and share her experience in research, which deserves one of the most esteemed awards for international scientists and researchers. Now I leave the floor to Professor Guadagnini and I go to my meeting, which is much less interesting than your conference. Thank you very much.
Good evening, and thank you to all of you for being here tonight to this exciting lecture. I'm very pleased to see quite a lot of young people, or at least people who look young, in the room. And especially since at Politecnico, in terms of research and education, we value a lot young talents and excellence. In terms of our strategic plan, that's a key cornerstone. We have actually 20 very exciting PhD programs spanning across all of the areas of the engineering, architecture, and design disciplines. One of the key elements of our research organization is to offer opportunity to young scientists and to young professionals like most of you in the room are, through the development of, I would say, excellent collaborations with the European level and also national level networks of strategic partners and universities. We are promoting on both individual projects for young researchers and collaborative projects and opportunities for all of them, actually for all of you who are here sitting in the room. And in terms of our activities, like I said, we are actively engaged in European level networks, promoting also talent academies with opportunities for sharing experience in several contexts, including laboratory infrastructures. We have actually developed our laboratory infrastructure strategy across several levels. We have laboratories at the Polytechnical level, so the university level, laboratory which are called interdepartmental laboratories, where a lot of interdisciplinary, multidisciplinary research has been, or actually is performed, and more vertical disciplinary laboratories in our 12 departments. I hope actually that, well, for sure some of you who are doing your PhD path here at Politecnico in Milano have already explored these capabilities in our laboratories. And for those of you who are going to start their master thesis project, I strongly encourage all of you actually to take advantage of these strong and unique opportunities. From a personal standpoint, I'm actually very curious to listen to the lecture of Professor Anne, especially because you're talking about attoseconds, and in my field of research I work with groundwater, and the responses of groundwater in terms of groundwater age are in terms of 100 years or millennia. So I'm very curious to experience the breadth of your talk. Also from a personal standpoint, and then I will close it up, just a little bit tidbit. That I had a conversation with my daughter yesterday. She's doing her PhD in physics, nanophotonics at USC, and she was very jealous that I'm at your lecture today. So we'll make sure to cherish every moment of your lecture. So thank you very much for being here, and thanks to all of you actually for also giving me the opportunity to address you at the very beginning of this exciting lecture. Enjoy. Thank you.
So I'm going to tell you about the route to attosecond pulses. So this will be a little historical talk. I will start by the background, the discovery of high-order harmonics, then progress and technology, very important, and understanding, measurement of attosecond pulses, which was done by my two colleagues, Pierre Agostini and Ferenc Ross, about at the same time in 2001. And then, very briefly, opening to other research fields and applications. So, nothing would have happened without the invention of the laser. I'm very happy today to give this lecture in front of one of the pioneers of laser, Professor Orazio Svetto. Ruby laser, and the Nobel Prize, the invention is from Theodor Maiman in 1960, and the Nobel Prize for, not for the laser invention, but for the background to the laser, was to Towns, Basov, and Prokhorov in 1964. So in our research, we are going to use two properties of lasers. One, the fact that we can confine the light in short pulses. And second, maybe more important, is that we can have intense radiation. Now, the laser invention opened new field of research. One of them is nonlinear optics, who started direct after the invention of the laser with the discovery by Peter Frampken in 1961 of second harmonic generation. So this is a process. This is not. Yes, you can see my pointer. Yeah. So this is the process where an atom absorbs two photons and then emit photons at a different frequency. In this case, second harmonic. And this is the experimental setup. Our setup are going to look very similar. You have a laser, a focusing lens, here a quartz crystal where the second harmonic is produced. Then you have a prism to analyze the radiation and a photon detector. The Nobel Prize to not only nonlinear optics but atomic spectroscopy, laser spectroscopy, went to Nicola Bloomberger. He's really considered as the father of nonlinear optics, and Art Shallow in 1981. And the third person to get the Nobel Prize that year was a Swedish scientist called Kai Sigban for the development of high-resolution electron spectroscopy. And it's interesting to mention that here, because electron spectroscopy is going to be very important for our research, as you will see. Now, the second topic that started after the invention of the laser is called atoms in strong laser field, very fundamental research, and in particular multi-photon processes that were predicted already in 1934 by Maria Goppert-Mayer. And here you have a two-photon excitation process. An atom is absorbing two photons and is excited. You can also have multi-photon ionization, where an atom absorbs several photons and then is ionized to detect the ion or the electron. In 1979, Pierre Agostini and co-workers discovered the phenomena of above-threshold ionization, where an atom can absorb more photons than what is required for the ionization. You can detect these processes by looking at the photoelectrons, by looking at, you see an electron that has this kinetic energy, and then another one. My thesis work, this is the beginning of the 80s, was to look at multiple ionization processes by multi-photon absorption. Here you have ionization of xenon, even 2+, by absorbing many laser photons. At this point, we thought that it was easy to ionize and to excite atoms when exposed to a strong laser field. So probably we were producing lots of excited atoms or ions in the interaction medium. So we thought we would like to look at the fluorescence emitted by this atomic medium. So we set up an experiment. So now we are in 1987. I just had become a researcher at the Commissariat Énergie Atomique in France. And so we set up an experiment. This is not working all the time, or is it?
Yeah.
It's okay? Yes? When I turn, I lose. Okay, anyway, I continue. So we have an intense laser pulse. We focus by a lens, and then we into a gas jet with many atoms, and we look. Fluorescence is emitted in all directions. So we had the idea that we wanted to look both along the propagation axis and perpendicular to the propagation axis. So we had two detection axes using a grating and a detector. And I'm going to show you a photograph of this first experiment. This is a photograph of the laser. It's a neodymium YAG laser, 1 micrometer wavelength, 40 picosecond. And it looks like this. You have the oscillator here between two mirrors. This is the oscillator and two amplifiers. When you look at this picture, I think that laser technology has actually changed and progressed. This is a picture of the setup. The laser is coming from the right. There is a gas jet. This is a vacuum chamber. You have the lens here, and again these two detection axes, perpendicular to the laser propagation axis and along the detection axis. You can notice that there is a printer here. This is before personal computers existed. Computers existed, but these were huge machines that were absolutely not available. So we were using a printer. The pen was coupled to the detector, and we were rotating the grating, and the pen was following what the detector was recording. So it's a long time ago. So what did we see? We did not see fluorescence light, and we saw nothing perpendicular to the propagation axis, so we'll forget that. But what we saw is very high order harmonics of the laser field. You have an example of one of the first spectra obtained in argon gas, and you see here harmonic 13, 15, 17, etc. up to 31. So each peak here means that we see light with a frequency equal to a multiple of the laser frequency. We are in the extreme ultraviolet region of the spectrum. We only see odd orders, and that's because of the symmetry of the interaction. It's a centrosymmetric medium, and because of symmetry, you don't have even harmonics. So if we plot the distribution of high-order harmonics as a function of order, you find this very characteristic behavior with first decrease and then this plateau behavior where all of the harmonics have this more or less the same intensity, and then there is a cutoff. And this was very unexpected at that time. It was unexpected for many reasons. The first reason was that we were thinking very much in terms of perturbation theory, and with an expansion of the polarization looking something like that. So this is a power expansion as a function of the electric field of the laser. So for such an expansion to be valid, you want the first order here to be much larger than the third, much larger than the fifth, etc. And this was not the case, because we had this plateau behavior with very similar intensity. So clearly, we are in a non-perturbative regime. So to understand this phenomenon, the first thing we do is we try to do simulations. And just to introduce this simulation, what is, I think, very interesting in this process is that it's at the border of two fields. The first one is atomic physics. You have the atom responds strongly to the laser interaction. This is described by Schrödinger equation, which you have here. It's rather simple, and in this time-dependent Schrödinger equation, and here you have the atomic potential and the laser atom interaction, which is here written in the dipole approximation. And in this field, we don't need to have a quantized formulation of the electromagnetic field. It's enough with a classical laser field. So think it's a sinusoidal wave. But the point is that these two terms are comparable with each other. Again, it's a strong interaction, which means that you need to solve this Schrödinger equation, the time-dependent Schrödinger equation. Now, the second aspect of this phenomenon is the response of the whole medium. This is called nonlinear optics, and it's described by Maxwell equations of electromagnetism, which can be simplified to a wave equation, such as this one here, where you generate a field due to polarization in the medium, polarization due to this laser atom interaction. So the first attempt to understand this process of high-order harmonic generation was to solve these two equations, and this is the result by Kuelander and Brushaw in 1989, solving the time-dependent Schrödinger equation and reproducing quite well, actually, the experimental behavior. This is a comparison of the yield of these different harmonics in xenon. In a sense, this was also a surprise, because we thought it would be much more and more difficult to have a good phase matching of the different harmonics. If I go back for a moment to this picture, you see here that to have a strong and efficient harmonic generation, you need that all of the waves emitted by the different atoms in the medium are in phase with each other, and this is called phase matching. So we thought that phase matching would be much more difficult to achieve for the high order harmonics. And it seems that this is not the case. So it was important to also solve the wave equation, which we did in 91, and we could reproduce more or less the experimental behavior with this almost like a plateau and the cutoff. Now we can simulate these processes. Doesn't mean that we really understand the physics. This took actually longer time. Now this is the time where the attosecond pulse idea was formulated by actually several people. You have two publications here. And it's a natural idea when you work with lasers, because this is the same phenomena that happen with mode-locked laser system. So the idea is the following. I'm showing here three waves, three different harmonics, 17, 19, 21. Let's assume that these harmonics are phase locked. What does it mean? That means that the maxima coincide at a certain time for all of the harmonics. And because of the periodicity of the process, after half a laser cycle, the minima will coincide, and then after another half laser cycle, the maxima will coincide again, etc. So let's assume that this is the case, and let's sum these different waves. So what do we get? We get constructive and destructive interferences, and because they are phase locked, at these times we get constructive interferences. In between these two lines we have destructive interferences. So we get a series of short light pulse. And if we plot, so here I'm plotting the electric field of the light. If we plot the intensity, we get this, we call it a train of very short light pulse. We are in the 100 attosecond range, 10 to minus 60 seconds. But the question is, are these harmonics phase locked? If we have not only 3 harmonics, but 10 harmonics, you can get even shorter pulses. This is an expression of Heisenberg principle. If you have 10 harmonics, you have a broader bandwidth, so you have a large bandwidth, you can get a short light pulse. So it's very undetermined in frequency or in energy, and very determined in time. So now I'm coming to part 2, which is progress in technology and in understanding. And I will start by progress in technology. This field of research has been really pushed during the whole time by progress in laser technology. At the beginning of the 19th, there is really progress due to 3 inventions that arrived approximately at the same time. You have the invention of chirpers amplification. It's a method to amplify laser pulses, led to Nobel Prize to Gérard Mourou and Donna Strickland in 2018. You have the discovery of a new laser material called titanium sapphire by Peter Moulton. And then you have a new method to produce short laser pulse in a laser oscillator, which is called Kerr-Lens mode locking. And in Sweden, in Lund, you have here 3 laser scientists, 3 scientists. They were doing spectroscopy before. They wanted to invest into new technology and to start a little bit a new physics in Lund. And they look at these 3 inventions and decide to put them together and to build the first prototype of this terawatt titanium sapphire in Lund, which I think was really a very clever decision. In parallel to that, there is progress in instrumentation in Saclay, where I was. We are building dedicated instrumentation to study high order harmonics, and you have a photo here of this instrumentation. This is me. maybe you don't recognize me, but a long time ago. And these are my first two PhD students in France, Philippe Alcourt and Pascal Salmier. So the principle is actually very similar to what I showed before. You have a gas jet, you have some optics to analyze the radiation, and then a detector. This is what we build here. This is also the time where personal computers arrived in the laboratories. They look like this, not very much like, it's still big things, but and we learned to program these computers, and we could acquire data in very different ways compared to what we did before. And this was very nice to, especially to work with this new laser system with a repetition rate of 10 Hertz. So this was also a revolution in experimental, how we did experiment. So what happened is that this Swedish scientists, they asked us if we wanted to come and work with them, use the laser system, and maybe we could take our instrument with us. And this is what we did, and we performed the experiment in Lund in 1992, which were very successful. And now the reason why I then moved to Lund is completely private research, but it's connected, of course, to this experiment. So this is one of the first results we obtained in Lund, and you see that now we can observe up to the 93rd harmonic in helium. So we are in the really extreme ultraviolet range of the spectrum. And as I said before, this is also thanks to this laser and thanks to this new way to acquire data, we could now follow how these harmonics depend on different laser parameters, on different parameters. For example, here, as a function of the laser intensity. Now, there was also, at the beginning of the 90s, a huge progress in understanding, and in particular with the discovery of what is called the three-step model. And this is really thanks to theorists. This Nobel Prize award is for the experimental method, but of course theorists have been important in this field of research. There has been really interplay between theorists and experimentalists. And this model was proposed at the same time by Ken Kullander, Ken Schaefer, and also by Paul Corcu. And almost at the same time, you have a quantum formulation of the model by Maciek Lewinstein and co-workers. And this is called the strong field approximation, has an impact in our field. So this is a simple picture of what is happening. You have an electron in an atomic potential, this Coulomb potential, but this potential is deformed, is distorted by the laser interaction on one side, so it's bent like this. This is what resulting in this deformed potential. So now here you have a potential barrier. There is a certain probability for the electron to tunnel through the barrier. Then the electron is driven away by the laser field. This is classical mechanics, Newton's equation. And the laser field change of sign, the electron is driven back towards the atom, and there is a certain probability for the electron to recombine back to the ground state. And in this process, you have the emission of high energy photons. If you consider all the different trajectories, you see that what you get is emission of light, pulses in the attosecond range. So maybe this was a little tough for some of you, the young students here. So now I'm going to make an analogy. You can take this approximately at the middle of this talk. You can take this as a small break, okay? No, you wonder what I'm going to say now, but and this is a small story. It's called The Adventure of an Electron in a Laser Field. So this is in Swedish. It's very easy. You replace C by K. Okay, this is a representation of this story. You have an electron in a prison, and this is nice, otherwise we would not exist. The electron is very bound to the nucleus. And on the side here you have a roller coaster. Okay, so an amusement park. I don't know if there are any in Milan. There are? Yes. So the electron would like to have fun. So now this is an exam to you. What does the electron do? I'm looking at the young people here. So what does the electron do?
From the prison to
He escapes, yes. How? You have to remember what was on the previous slide. So how does the electron escape? I think I heard tunnel, yes. Okay, this is not finished. So these are my own drawings, which yes. Yes, the electron is free and is very happy. Is in this roller coaster and is going up and down in the laser field. Okay, this story is finishing very bad. The electron is meeting the prison, which is open, and just falls. And in this fall, it has a lot of energy. The energy is transformed as a scream, which in the other story is a light pulse. This is end of the story. So this was a small break. Now you're ready to continue. So what happens to the attosecond idea? So this is just a recap of what I said before. Phase-locked harmonics is equivalent in the time domain to a train of attosecond pulses with one pulse per half cycle. So this is a little bit what we would like to have. Now we can calculate this using this better understanding, and in particular this strong field approximation I just mentioned, and this is what we get. It's much more complicated. Sometimes when you progress in physics, you don't have really the answer that you expect. So you have light a little bit all the time, and you have especially two pulses per half cycle. And if you look at the process, we can actually understand that by just looking at the possible trajectories. And it's very easy to convince yourself that you have two families of trajectory. You have trajectory where the electron is going away from the nucleus, but coming back almost immediately. And the longer trajectories where the electron is emitted actually a little bit before, relative to the laser cycle, and comes back, have a much longer trajectory. We are talking about excursion of the order of nanometers, and then return with approximately the same energy, and this is giving these two peaks per half cycle. So this means that the harmonics are not phase locked. You can plot the relative phase of the harmonic, and you get something that looks like random. This is not working anymore. Yes, working a little bit. You have a phase look random, except at high energy, but this is the cutoff region where there is no photons anyway. So the phases look random, harmonics are not phase locked. Okay, we are a little bit disappointed, but we continue to study this phenomena, and at the end of the 90s, we performed an experiment in Lund where we study the coherence of high order harmonics. And this is an experiment performed with, here you have another old photo with myself on the right. Mette Gorde was my first PhD student in Lund. Ted Hensch and Marco Bellini from Florence. So this was important experiments where we, so what we did is very simple. We make two replicas of these attosecond sources, and then we look in the far field. So and if they are, so you have light, which is diverging, and if this is coherent, you will have interference. So this was the idea of the experiments, rather simple. And this is the result that we saw on harmonic 15. We see very nice interference fringes. But what you also see, and this is the first time this was really seen in experimentally, is you see two regions of emission, a collimated region and a more divergent region. And we can identify these two regions as due to these two families of trajectory, short trajectory and long trajectory. The reason is that is related to the phase which is accumulated by the electron on its trajectory. Almost no phase in the case of short trajectory, and a longer phase due to the long trajectory, and this is going to affect the wavefront of the light that is generated. Almost nothing on the short trajectory, collimated radiation, and a strong wavefront on the long trajectory, this divergent beam. We could also vary the delay between the two sources, for example here by 15 femtosecond, and you see that the fringes have disappeared for the long trajectory, they are still present for the short trajectory. So these two contributions have different physical properties. And if this is the case, that means that we can also control and maybe remove one trajectory relative to the other. One obvious thing that you can do is you can aperture the beam in the far field and then you kill this long trajectory. And this is what Pierre Agostini is actually going to do in his experiment when he will measure the attosecond pulse duration. He will have an aperture and then killing the long trajectory. We also make progress in understanding the second aspect of this phenomena, is nonlinear optics. If you want to have phase matching, you would like to have the phase velocity of the fundamental field equal to the phase velocity of the field which is generated, same refractive index. So mathematically you can express that by saying that the phase mismatch between the polarization in the medium and the generated field should be equal to 0. The phase mismatch depends on the dispersion in this partially ionized medium, depends on the laser focusing, and it also depends on the electron trajectory. Same story, this phase accumulated by the electron, which is then transferred to the field, to the electromagnetic field. Again, you see that the condition delta k equals 0 depends on the electron trajectory. So maybe in certain condition you can phase match one trajectory and not the other. And indeed, we could show numerically that in some conditions you recover the simple picture with one pulse per half cycle, which means that we have phase-locked harmonics. So now we are at the end of the 90s. We have this attosecond pulse idea. It's not so clear that, yes, we have attosecond pulses. We think that in some condition, maybe we could have attosecond pulse, but we don't know for sure. So this is why the measurement of the attosecond pulse was so important. I want just to summarize a lot of things that was happening at the end of the 90s. The first thing was actually happening here. This is progress towards few cycle pulses with pioneer work by Moro Bisoli here. And also at the same time you have the realization, the understanding that the carrier envelope phase of the pulse should play a role, and also how to control this carrier envelope phase. You have progress in the geometry of the interaction. What kind of gas medium should we choose? Should we choose a cell, a jet, a capillary? So there were really a lot of research around that. Even new media were used, like molecules, and this was going to be a new field of research in itself later on, called atomic spectroscopy. There is also progress in using different laser systems, higher photon energies. We could get higher photon energies by using short pulses and also a long wavelength laser. This was pioneered in '99, and this is a later result, but showing harmonics up to more than 1 kilo electron volt. And finally, there is also a push towards higher pulse energy, in particular in the group of Midorikawa in Japan. So now I'm coming to part 3. This will be very short. I'm just going to actually have one slide to explain the method. So measurement of attosecond pulses. And again, this is the work of my two colleagues, Pierre Agostini and Ferenclos. So both used a cross-correlation technique where you study your XUV pulse or XUV pulse trains using actually the infrared laser electric field that is used for the generation. So I'm going to explain only one of these techniques. They're actually very similar, and it's the technique used by Pierre Agostini. Pierre Agostini could characterize attosecond pulses in a train of pulse, while Ferenclos produced also isolated attosecond pulse and characterized this isolated attosecond pulse. So let me present to you the technique developed by Pierre Agostini. And so I'm going back to this type of scheme with which I started. And here I consider two photon ionization using harmonic, fused harmonic, and then a laser photon. So it's two photon ionization. You detect that by measuring the electron energies. You get two peaks. One is the main peak, and the second one is called sideband. Now you can use, and this is an idea from the theoretical group of Alfred Maquet in '96. You can also reach the same final state here, this sideband, by absorbing one more harmonic, the next one, and then you have stimulated emission of one laser photon. This technique is called rabbit, which means reconstruction of attosecond beating by interference of two photon transition. So you see that now we do a little bit of quantum mechanics. You have the same final state, which is reached by two quantum paths. This one and this one. We are in quantum mechanics, we should add amplitudes and not intensities. So the signal that you get is going to depend on the relative phase of these two amplitudes. So let's look at which phase are involved in these two quantum paths. And you have first, you have of course the phase of the harmonic, which I'm calling phi q. And then you have also a phase which is due to the ionization process. This phase is going to be an important application of attosecond science, but let's forget it for the time being. We assume it's very small, which is the case in very often. Now you have the phase of the next harmonic, and now you have the laser field. So laser field is delayed compared to the harmonics, delayed by tau. So you have a phase which is omega tau in this path, and the other path, since it's an emission process, is minus omega tau. So the signal that you get is an interference signal, it's interference of these two quantum paths. And in this cosine term, you will have the difference of phases. So you have phi q plus omega tau minus phi q plus 2 minus omega tau. So you have this equation here. So you see that by varying the delay, you have a signal which oscillates. It's called rabbit signal. And the position of the oscillation give you information on the phase difference, which is what I want to measure. And this is the result of the first experiment of Pierre Agostini. So this is the phase difference between consecutive harmonics. It's not flat, which means that the harmonics are not strictly speaking phase locked. There is what is called a chirp, but it's not random. It's some linear variation. And if you use that now and use the information on the intensities and go into the Fourier, make a Fourier transform and go in the time domain, this is the result obtained, showing for the first time that this combination of higher order harmonics was in the time domain a train of very, very short light pulse of duration 250 attoseconds. So now I'm coming to the last part of this talk. I will say just a few words about what you can do with attosecond pulses. And I will show you two different applications. One which is very fundamental, and we will just use a very simple atomic system, and it's the idea to measure the motion of the electron dynamics using attosecond pulses. And then I will also show you much more applied applications. So we start by this idea: can we use attosecond pulses to measure the dynamics of the simplest possible process, photoionization, which was it's the photoelectric effect, which was explained by Einstein in 1905. So this is actually why he got a Nobel Prize in 1921. So I'm sure you have seen this process before. You think of photoionization and due to X-ray photon. And I'm sure you think about this electron leaving the atom as a particle, right? Going to a detector, and the detector measure the energy, possibly the momentum of this particle. But we are in quantum mechanics. This particle is also a wave. So really what we can do with this attosecond techniques is to measure the wave, possibly quantum properties of the photoelectrons. So, and there are really two ways to do that. One way is to consider a very broadband excitation. So think that you excite an atom with an attosecond pulse, and you create an attosecond electron wave packet. It's very, very broadband. And what we can do with this rapid technique that I just mentioned we can measure the relative phase, the spectral phase of this attosecond electron wave packet by making this measurement, looking at the side bands and measuring the phase and see how this phase is varying as a function of energy. And here I'm not looking at the phase of the harmonic as I did previously. I'm looking at this other term, the phi q at, which is due to the ionization process. The other way to use the same technique is in the case of where we have a resonant process. And here we create an attosecond, we create an electron wave packet, not really attosecond, in this case it's femtosecond, but we create an electron wave packet and we want to measure its phase. Same idea, we use this quantum interferometer to measure the phase of this electron here, which can be affected by the presence of a discrete state. So this process is called autoionization. You can ionize an atom here by photoexcitation and then decay to the continuum, or directly by photoionization. So it's again an interference process leading to strong interference and strong phase variation. So with this technique, we can maybe look at the phase of this auto-ionizing process. So I have chosen to show you some results on this part. So this is obtaining helium. So again, it's the same excitation scheme. And thanks to this scheme, we have access to this phase variation due to this interaction with this discrete state. And what do we see? We see a strong interference phenomenon. This is for the amplitude. And this is the phase where you see a variation of pi across the resonance. And we can use this to really follow in time the ionization of the atom. And this is a Wigner representation of the interaction, some kind of time frequency representation. And you see that here we have a broadband direct photoionization. This is a very fast process. It's typically a few femtoseconds or less. Then we have a strong interference structure that develops due to this interaction with the quasi-bond state. And in the end, it's more photoexcitation, which then decays towards the continuum. Now, to conclude, I will maybe show you much more recent research that we try to do in Louis. So now I'm finishing this talk by a little bit what are we doing now. This was a long story, but where are we now? Now we really try to we think, okay, we measure the phase and amplitude of the photoelectron. Is it always the case? Do we always have a coherent electron wave packet? The answer is no. This is not always the case. Now we are really towards quantum information. Maybe we don't have a pure state, coherent state. We could have a mixed state. So can we measure this quantum property of the photoelectron? We need to do a tomography of this electron wave packet to measure the density matrix. How can we do that? And here we propose a technique which we call Kraken, and which consists in measuring this density matrix. And the idea here is we create a wave packet that you see here, broadband wave packet, and we try to analyze this wave packet with a bichromatic probe field. Instead of doing like this is the rabbit technique, we do like this with slightly two different colors. Same idea, we have a quantum interferometer. This time you have this path or this path. This is two photons of the same broadband pulse. Okay, but we can go to this final stage using this or using that. And now if we study the signal at this energy as a function of the delay, we will have also an oscillation. And now the oscillation, the signal will vary something like this. Again, interference signal, but now it's not 2 omega here, but delta omega, omega 1 minus omega 2. And the contrast of this oscillation is going to depend on whether there is a phase relationship between these two states here of the wave packet. If there is no good phase relationship, that means that we have lost some coherence. Okay, so the contrast here tells us about the coherences, and we can also measure the phase. So this way we can measure for a certain omega 1, omega 2, we get a sub-diagonal of the density matrix. This is a representation of the density matrix obtained in helium, so you have energy on this side and energy on this side. This is continuous variable. So we make actually 7 measurements, then we have the diagonal, and then it's just a mirror image of the diagonal. You can see that this is rather round density matrix. Then we can do some interpolation using something called Bayesian optimization procedure, and this is the result. No surprise, this is a pure coherent state. We do the same experiment in argon, and this is what we get. So now it's not at all round, it's an oval result, oval density matrix, which means that here we lose some coherence. And the reason for this is something called the spin-orbit interaction, leading to 2 different ionic states, and which means that the wave function of the total system, ion plus electron, is actually a sum of 2 states, so it's an entangled state where the ion can be left in state 1/2 or in state 3/2. And since we measure only the photoelectron and not the ion, we lose information, and this is what leads to this mixed state for the density matrix. Now I would like to again conclude by completely 2 different applications, but this time is really applied, and I would say in the hands of the industry, and this is a semiconductor industry. It's to use these high order harmonics. We are not talking about attosecond pulse. They really don't care about attosecond pulses. They just care to have a broad bandwidth, to have coherent light with a broad bandwidth and many frequencies at the right wavelength, which for them is in this extreme ultraviolet range, around 13 nanometer. So the project is to use this source to image, to analyze the computer, the silicon wafer on which you have lots of components, both in 2 dimensions, but also now in 3 dimensions. They want to stack many transistors. So the technique is some kind of diffraction technique. So this is a project by the big company in Holland called ASML. So I'm actually very happy that now these high harmonics can be used for next generation telephones or computers. What is the next chapter in attosecond science? I think there is a lot to do, and I have seen many experiments actually in Milan on this using this attosecond pulse time scale to look at electron dynamics in more complex systems like molecules or condensed matter. Since 2 or 3 years, there is a new source of attosecond pulse in free electron laser with different properties. These are much higher energy photons, but it's easier for them to produce a single pulse. Now, now I'm really coming to my conclusion. If you have the chance to be a little bit at the right time, at the right place, 37 years ago, you might end up here. And so this is the Nobel Prize ceremony on the 10th of December in Stockholm. It's a very nice ceremony. This is the royal family that you see here. You have Alfred Nobel here. And these are the happy laureates. And maybe you end up like this. Hours later, there is the banquet. It looks like this. In the Stockholm City Hall, you have 1,300 guests. And also a very interesting experience, especially from people from France, educated with the French Republic and the French Revolution was a very interesting part of French history. And spending 4 hours together with the King of Sweden was yeah. I would like to, of course, all this research is not done alone, it's done with many, many people over the years. This is the present research group in Lund. They are not, their clothes is a bit different normally. They are also celebrating the Nobel Prize ceremony on the 10th of December together. You have a lot of founders here. I think I would like to thank Moro for this organizing this visit. And if you are interested by Attosegan pulses, I really encourage you to go to this Attosegan Research Center in here. And thank you very much, Moro, Orazio, Sandro, Katarina, all the new generation. And they are really trying to push Attosegan science in complex systems, which is very important. Thank you for attention.
Thank you very much, Sam, for this really nice presentation about the history and also the future of the Attosegan science. Now, please ask questions to Anne. It's a unique opportunity for you students to make a question to the Nobel laureate. If you want, I can start with a very simple question for you, Anne. In your view, which is the most interesting direction of research now in Attosegan science and technology?
I think there are many interesting directions, which is very exciting. You have. I am a little bit fascinated by this quantum aspect. I have no idea where this will lead, but I think it's exciting to become a little bit closer to quantum information, so that's very interesting. This application in the semiconductor industry is fantastic. I mean, if this radiation I have contributed to discover 37 years ago is useful for everyday life, would be fantastic. And then what you are trying to do a little bit in Milan, which is to go to a little bit more complex system. I think this is the challenge and the main application of Attosegan science in the years to come. So this is terribly important. So I've given 3 answers.
Thank you, Anne. Question, please, student. Yes.
Thank you for an interesting lecture today. And the Nobel Prize is awarded to people who have pioneered new and original field. But how do you think truly unique research emerged?
I would say a little bit of luck. Curiosity. Maybe this is the right answer. We were motivated by trying basic research, understand the behavior of atoms in strong laser fields, and we have an idea, and then we saw something different but very exciting. So I would say it's not completely out of a hat. It's the following of actually many years of research. And this above threshold ionization I mentioned at the beginning was some kind of pre-experiment to this as well. So, and then of course you need, when you have this result, to of course continue, which is also important. Yeah. But I would like to stress the importance of fundamental research.
Hello, I'm not a student, I'm actually a colleague of her father. I'm also a student and my students are here. Thank you for this extremely inspiring talk. I have a question regarding the past. If you, of course, I have to take this opportunity to ask you, if you look back, is there anything you would have done in a different way, or you think it could have been, you could have discovered faster things? Thank you.
This, I don't know, honestly. It's clear that it took a lot of time it took 14 years to from the discovery of the high harmonics. Just a couple of years later, you have the idea, are they attosecond pulse? But then 14 years to measurement of attosecond pulse. And the reason for that is that we were trying to measure attosecond pulse, but we were using autocorrelation. And this was really very, very difficult. It's still not possible to do that today, or it's still very, very difficult. And so we went into a wrong direction, most of the community actually. And then you have this very important measurement in 2001. So I don't know, I cannot say, oh, we should have done it differently, but I just want to say that it took time, and this time was probably needed. Yeah.
What are the priorities to reach the gender equality, and has been Roland influence your work?
I can't answer about the priority. I want to give a little bit optimistic answer. The 40 years I've done research, I think this has changed. I worked during many years with only men, and now this is not the case. In my research group there is about 30% women. I have also seen that with students. I think the classes, engineering physics, there are more and more women. 5 women Nobel Prizes in physics is not very many, but the last 5 years you have 3, so this is already much better. 2 in 120 years and 3 in 5 years. So I want to be a little bit optimistic, but I think it's very important to continue to be aware of the inequality and try to do everything which is possible without going too far to help. Yeah.
Thank you so much for your lecture. I was particularly interested because you mentioned that you are now interested in applying the attosecond research on quantum information research, and I was interested specifically how, so like on keeping the coherence, or on how to measure the phases and so to obtain the information. So I was a bit more interested in understanding how you could apply this theoretical research on quantum information research. Thank you.
Yeah, this is not what I showed were really experiments, so we are doing that. I don't think we are going to help quantum information research. I think it's just the opposite. I think quantum information is going to help us understand better, maybe spectroscopy of atoms and molecules. So this is what I think it's going to be this way. But it's really just the beginning. So we are developing methods at the moment, and we are talking to the physicists in quantum information to maybe help us to ask the right question.
Thank you for your great lecture. I have a question of interest, actually. Do you think that the attosecond pulses can help to actually realize better the decoherence time of a pure state in quantum mechanics?
I think this would be great. This is for me. It's one of the possible goals. I cannot say that this is what we are going to do. But what would be great is to now we start to be able to measure this density matrix. Can we have a and of course we have very short pulse, so you have, can this be done time dependent? So yes, would be very nice, but this is really the beginning, so yes.
Other questions?
Just a quick question. You were mentioning, I saw in the future applications, magnetism, magnetic fields, imaging. Maybe there are already interrelationships with the medical sciences fields. Can you say a few words about that?
I think this is really more in the future. My colleague Fernand Klaus is trying to develop medical application or diagnostics. But it's not really using attosecond pulse, it's using actually the electric field and the control of the electric field with attosecond precision. So it's going into these directions. Now to use attosecond pulse themselves for medical sciences, maybe in some future, I don't know. But there is a lot of fundamental research to be done first.
Anne, excuse me, what do you think about attochemistry?
Yeah, I think for me, attosecond chemistry is really what happens at the beginning of a chemical process, and I think this is obviously again a challenge of attosecond science to show that you can measure, possibly control what happens at the beginning of a chemical process, which is triggered by an electronic transition. So I think this is a huge challenge in attosecond science to be able to do that. And this is probably where you will have applications.
Very complicated. Other questions? If not, we can close this lecture and we can thank again.